Friends, Romans, DAC attendees, lend me your ears. We're here for day 3 of the Poster Gladiator competition that's part of the 59th DAC engineering track. We have 3 final presenters today. I know some of you in the audience have been here yesterday, some of you have been here 2 days. So thank you for coming back, and for those who weren't and came today for the first time, thank you for coming. We're going to have some fun. So we're going to hear from 3 poster presenters. They have a total of 10 minutes to present. Our august panel of judges then peppers them with questions, and then we move on to the next one. And at the end of this, we're going to tally up the votes, and we're going to announce a winner, give or take around 5:15. If you go to the DAC app on your phone, you'll see all the way down at the bottom the Poster Gladiator session. You can click on that and you can vote for your favorite paper. So get ready for that. Let me introduce our august panel of Roman judges. Each of these gentlemen has been a past chairman of DAC. On my left, Mac McNamara, Rob Aiken, Shwali, and Harry Foster, each brilliant in their own right, and they could have run Rome themselves. All right. So enough housekeeping. Let's kick it off. We are going to start with towards an automated workflow for link level exploration and optimization in the domain of all-to-all optical networks, and that's going to be presented by Ahsan Alam. Welcome, Ahsan.
Hello, everyone. The title of my talk is Towards an Automated Workflow for Link-Level Exploration and Optimization in the Domain of All-to-All Optical Networks. The work was done by Dr. Luca Ramini from HP Labs and myself. Unfortunately, Luca couldn't be at the conference this year, so I'm going to present on his behalf. So I'll start by giving you some motivation behind picking this project. So I know that a lot of you have been hearing the terms machine learning and artificial intelligence over and over in the keynotes and in a lot of the other presentations. And that's because these technologies are becoming pervasive in our modern day technologies. And one thing that's pretty common between them is that they both require the transferring of a huge amount of data with a very tight latency profile. And this is posing some serious challenge to traditional all-electrical interconnects. And this is where all-to-all optical networks that uses silicon photonic devices and optical fibers can provide a solution. And so this is why HP Labs have been focusing on these optically connected all-to-all networks. In the picture on the right-hand side, you can see one such network that has 9 nodes. And the key thing about these networks is that any compute node here, which can be either a CPU or a GPU, can connect to any other node in the network via a direct optical fiber link or a pass-through optical fiber link. Now you can easily imagine that the performance of the network critically depends on these links. And so being able to reliably design these links is very important. Unfortunately, the current design process for these require a lot of expertise from the circuit designer. Even for an experienced photonic circuit designer, this can require a lot of tweaking that has to be done manually right now, a lot of back and forth, trial and error, so the whole process can be time consuming. And this is why we are proposing this automated workflow that will use ANSYS's photonic circuit solver interconnect along with the optimization tool OptiSlang for link level exploration and optimization. So the main idea is to give the photonic circuit designer the necessary tools for this task. so that they can pick the best design easily to meet their needs. To test our workflow, we picked a test case. So we picked a 4-channel WDM link. The schematic you can see in the image on the left. It has a 4-wavelength comb laser feeding the transmitter, which is composed of 4 ring modulators. Signal goes through an optical fiber, and on the receiver side, you have 4 ring filters to demodulate the signal. For the exploration, we picked 6 design parameters for the whole circuit. The 4 bias voltages for the 4 ring modulators, the quality factor for the transmitting rings, and the quality factor for the receiving rings. And for the response of the circuit, we looked at the bit error rate for each channel with a goal to minimize them. So now let's see how we can transfer the sad designer who is doing the manual approach into a happy circuit designer who is going to use the automated approach. The way the workflow works is you first start with interconnect, and you set up your circuit just like you are doing right now in your manual approach, but you would do it in a parameterized way. So you will have your high-level parameters, and as you change your design parameters, the circuit behavior will change. And then you will also have some analysis script to analyze the results and automatically extract the figure of merits, such as the bit error rates. Once you have your circuit prepared, you go to OptiSlang, and this will be your cockpit for both the exploration and the optimization. The first thing you do is you create a meta model or a reduced order model for your circuit. And to do this, OptiSlang can automatically launch multiple interconnect simulations, adaptively change the different parameter values. And what it does is it links the relationship between your input design parameters and your output. In the end, gives you a reduced order model for your circuit. Once you have this reduced order model, you can go to the optimization stage and launch thousands of design calculations within a matter of minutes, because you're doing this calculation using the reduced order model. And this allows you to easily pick the best design, and you're done. So let's see what results we ended up with. So the nice thing about this workflow is even before you go into the optimization stage, you can first do the sensitivity analysis, and in that process, you can get some deep insight into your circuit. The table that you see on the right-hand side is called a COP matrix. It gives you the relationship between all the outputs as a function of the input design parameters, which are on the x-axis. And if you look at the plot, you'll see right away that the Q factor for the receiver rings play a major role in determining the bit error rate, whereas the next column, the blue one, is the Q factor of the transmitting rings, which doesn't have almost any effect. You can also see that the bias of the 4 rings in the transmitter plays some role in dictating the bit error rate. So this type of insight is developed over years of experience running simulations, doing tape-outs. It's really nice that you can launch these simulations from OptiSlang into interconnect and get these insights very easily. And of course, once you have done the optimization, you get your best design. Here, we get multiple best designs. And so with one optimization, you can have multiple best designs that you can see in the red dots here. So depending on your application, you can pick one of those dots that gives you, that meets one particular criteria. If your design criteria changes, you can just quickly pick another design, and you're set. You can get the design parameters and responses for your best design, whichever you choose. So to give you kind of like the final output of the investigation, we saw 1 to 4 orders of magnitude improvement in the bit error rate across all channels, with the biggest improvement in channel number 2, where we went from 0.28 to 5.7, 10 to the power minus 5. And this whole process took only 10 hours in a laptop with 6 cores. So to summarize, we're proposing an automated workflow that uses interconnect and OptiSlang for link-level exploration and optimization. For a proof of concept, we looked at a 4-channel WDM link that can be used in all-to-all optical networks. We did a sensitivity analysis to create a meta model, and then did an optimization analysis. We picked some design parameters, explored their effects on the circuit, and optimized the response, which is the bit error rate. And finally, we improved the bit error rate for all channels from 1 to 4 orders of magnitude. We are really excited by the success of this workflow, and we are continuing the investigation. The next step is to try it for a bigger system with 16 channels or more, and then see how the workflow scales with the size of the circuit. That's all I have. Thank you for your attention, and I welcome any questions.
Thank you, Ahsan. That was awesome.
Yeah, so you give improvements in terms of the bit error rate. Now, earlier on, you had a slide and you talked about certainly you could do this manually, but why would you? You'd want to do it automatically. What is the overall improvement in terms of, the amount of effort, the amount of time spent doing it manually versus now that we do this automatically?
I believe it's going to be a significant improvement because the first stage where you're setting up your circuit, you are doing that anyways. Even if you're doing manual tweaking, you will have to set up your circuit in a circuit simulator. And then the second and third step, from the designer point of view, it takes very small amount of effort because the tool has these wizards that you can launch and just pick your design parameters, pick the range over which you want to vary them for. And then the tool will automatically launch multiple simulations and change the parameters in an adaptive way. So it kind of runs the simulation, gets the responses, and decides how to change the parameters in what way. So as a designer, it frees up your time that you set up your circuit, you pick your design parameters, but then you launch the tool on Friday night, you come back to your desk on Monday morning, and you have your meta model created. And you get that insight to your circuit, right? That which design parameters are critical and which are less important, so you can simply ignore them. And you go to the optimization, which as I mentioned, since you use the meta models, it actually just takes a few minutes to do the optimization part in the end. Whereas for the manual process, depending on the complicacy of the circuit, it would take days or even weeks. So it's a significant improvement.
And the numbers that you're changing are the bias voltages and so on?
Yes.
You're not moving the frequencies of light or changing?
Yeah, so here, we are, the carrier frequencies are fixed.
They're fixed.
And so we are simply shifting the resonance. We can potentially shift the resonance, so that's what we're doing with the bias. So if you imagine the resonance shape of the ring modulator, by changing the bias, we are kind of shifting the operating point. And so you want to operate on a region on your curve so that you have the maximum extinction ratio. And then that way you can reduce the effect of noise on your signal.
Okay, because that was my next. Are you going to then, when you implement it, you'll have maybe different lengths of channels between the nodes as it's actually manufactured? You might have to tune it again, or is this golden numbers that you can go for deployment?
So sorry, yeah, you mean when you say length of the channels?
Well,
you mean kind of the
when you
spacing,
build
or?
this, will there be a manufacturing variability that you now need to tune the network again for?
Yeah, no,
for
that's a very good point. Yes, there definitely is going to be manufacturing variability, right? So that's definitely not part of this particular study. But the tool that we have used, Interconnect and OptiSlang, both of them has, say, built-in Monte Carlo sweep so that you can account for manufacturing variability. And in OptiSlang, you actually can do robustness analysis. So when you set up your circuit, you can set up these what we call statistical parameters for the compact models of the ring, which can capture, say, for example, the width variation in the ring or the doping profile variations. And from OptiSlang, you can then change these delta parameters in your model and then again launch more simulations to do some robustness analysis. So what you should do is you should first pick a few best designs that meet your needs and then do robustness analysis on them and then see which one is more robust and just pick that.
Yeah, that was basically going to be my question is how can you tell if you're at a stable or an unstable kind of optimization point? And it sounds like potentially with the robustness analysis you could do that.
I believe yes, robustness analysis would be the way to go. The catch is that you need to first collect silicon data for that. So you have to start with fabricating a lot of those rings, see how they vary from one fabrication to another, and then build that into that compact model, which was the building block of your circuit in interconnect in the first place. And we have flows to do that. You just have to do a lot of fabrication and get the data in the first place. And then you just go into your simulation and you can do this type of analysis. Like the capability is already in place.
Okay, but if you didn't have any silicon data and you said, well, this is going to vary, I'm going to just stick my finger in the air and declare this will vary by 5% and construct a model that way and see what happens, would that work?
That is definitely one way of doing it. So, even if you don't have silicon data for your rings, you can have you typically have a lot of data for your line width variation as you fabricate these waveguides. So you can actually build your compact model based on those physical parameters. If you know how the line width is going to vary, if you know how the wafer thickness is going to vary, which is already available to foundries, you can build your model based on those information and still have some manufacturing variability included in the model, which typically would be enough, at least for a first run, and you see how robust and how close your design is.
All right. Time's up. Thanks so
Thank
much.
you.
Let's give Ahsan a round of applause. Next up is dynamic CDC verification with enhanced jitter modeling in synchronizers from Youngchan Lee. Welcome.
So today's topic, my topic is dynamic CDC verification with a little enhanced jitter modeling. So here I will compare traditional synchronizer jitter skew model compared to with some enhancement to model the very special situations. So let me explain. So typically, the upper right side of schematic shows traditional synchronized jitter model. So there is a kind of in-module modeling of meta stability of the first flap of synchronizer. Typically, designers typically use this model to model this the meta stability and to check any problem under the meta stability problem. But as you know, somebody might know this model, this kind of style of model has some limitation. When sometimes we can inject some false injection, or it does not catch some special, something like short pulse or combo glitch checking. The key point on this slide is this traditional model has some limitation. So I will show you what will be the difference. If we add some more defined model, we can capture some different problem. So this slide shows. Here, there is no problem. To refine the model, we have to monitor. So in this slide, the synchronizer model shows the inside of the synchronizer. So with that information, we cannot monitor what are happening outside of the fan-in cone of synchronizer. So to enhance the model of the synchronizer jitter, we have to monitor the fan-in cone logic in the figure. So for example, what is the fan-in cone logic? What kind of combinational logic are there in the input? And is this the source clock synchronous or asynchronous? So by adding this more enhanced, more detailed information, we can increase the accuracy of the modeling. And I will show the different situation. The number one in the number one diagram, diagram shows the typical purpose of the jitter modeling in synchronizer. So here we have the simple situation. At the rising clock of rising edge of receiving clock, there is some change. That will be the target of jitter skew modeling. But with the traditional modeling way, so in case of number two, see carefully, number two and number three, in case of number two case, there is a short pulse between receiving clock edge. But if we see the situation inside the model, we cannot know what is happening outside the model. So because the input toggling and receiving clock are asynchronous, so traditional model cannot detect this kind of situation. Another example of the number 3 case. Number 3 case shows, for example, in the panning cone, the register 0 and register 1 toggled simultaneously, and if there is a combination glitch, and accidentally, the glitch is captured at the rising edge clock of the receiving clock, rising edge. That will cause any severe silicon problem. So the key idea is we have to model to detect this strange situation. We have to monitor the outside of the synchronizer. That is the key idea, and so to model this kind of situation, we are using the traditional static CDC analysis. Based on that, with the tool of CDC tool, with the help of CDC tool, we can extract many information, synchronizers and panning code logic. And based on this information, and we include after clearing functional verification without any meta-stability effect, we can then include those models on the test bench top and then run all the simulations many times with different shader because we need more severe randomness. So this is something like marathon, because without any meta-stability effect, that is just he's running on a clean day. But we need to verify that the marathoner can run under the rainy season, hot weather, very hot, with the hot stress, tough situation. So the next one, here is some example of the real design bug. When with this stress injected, we can these modeling revealed some real problems in our design. So the first one is to synchronize. There are 2 synchronizers, and it is converting and it is controlling some funny state machine. But there is really in the circuit between 2 synchronizers, and it is touching the funny state machine transitions, and the designer didn't know didn't know what happens under the meta-stability stress. So this kind of, the second one is this is a little stupid. So there was a combination of glitch in the synchronizer input. It captured accidentally with this combo glitch problem. Normal simulation will not reveal this problem anyway. That is true. The third one shows the source side is sending a very short pulse, but somehow the pulse missed in the receiving side. But somehow functionally it didn't have any problem, but in some situation with various scenarios it can cause some problem in our design. So summary. So here the important point is the traditional model has some limitation. So we need to enhance more. We need the model should reflect more refined situation, very special case. There is the one point, and another point is to achieve this goal, we can reuse our previous ready prepared CDC sign-up flow. On top of that information, we can extract some models. We can add add those information during simulation, the verification based on simulation, we can reveal many kind of problems that is hard to detect during normal simulation. And so time is almost up. So I think I have covered the important key points only. So that's all for my presentation.
Thank you so much.
Let me know if you have any questions, so I will explain.
So do you have any notion of how many bugs you've found by running this? Before you just use a simple model and then you applied this dynamic CDC and
Yes.
and what was the improved design flow? What was the quality of the chips?
So with this model, maybe we will not find any lots of problems. That is the very stupid situation, but it is true. With normal simulation, we will not never see those bugs. We cannot detect them. But
I mean, they're metastable, right? So there's something that would be an unreliable system.
Yes.
Because these typically would not be reproducible. It would just be not very reliable. But then maybe if you designed with this, you had more reliable systems. Do you have any sense like that?
we can. So could you ask?
After doing this, were your chips working better in the field? They were much more reliable now that you eliminated this clock domain crossing problem?
Sure,
Did you have a sense like that?
Sure.
Yeah. I was looking for
Yes.
how did it improve the reliability of the product?
Yeah, or maybe another way to word it, what was the original motivation for doing this? Why did you decide to do this?
Motivation for this work.
Yes.
Because we have find several cases that is hard to detect.
Predominantly reconvergence, I assume, or predominantly reconvergent type issues?
Yes. But that will depend some scenario dependence. But once the scenario touch that point, the problem will come to us.
How long does it take to run this tool? So when you run static, it's usually fairly quick, and dynamic is usually slow.
Yeah.
How long does it take to run the dynamic CDC?
I think it will maybe 15 to 20 overhead, simulation overhead.
But again, the key to this is achieving good coverage. Otherwise, you don't know what, you don't know if you actually test this scenario in terms of reconvergence.
Yes, it depends on the scenario. That is the weakness of simulation. But if we can do this with the formal, with the really good machines, then the problem we can prove that there is no problem like this.
All right. Let's give Youngchan a hearty round of applause. Thank you so much. All right, the suspense is building. We have one more, and then it's voting tally time. So get your apps ready. Start voting. Last but certainly not least, pre- and post-silicon analysis in the design and validation of AI-enabled high-performance microprocessors. This will be presented by Nagu Dhanwada. Welcome.
So this is a topic, I think, which all our keynotes touched on, AI, accelerators, and energy efficiency. I'm here to talk about the work we did in terms of in IBM systems and research, in terms of how we take actually realistic complete workloads, and then use it to assess the efficiency of accelerators, inline accelerators. So that's what this work is about. All right. So here is an overview slide which actually describes the work. So what we are talking about here is a framework that can actually run complete workloads, right, at an early stage of the design and actually influence the first step of your design, right? As the chip is being designed, you're actually running complete workloads and you're trying to influence the state of the design, okay? and use that, also have a framework. So that's the early part of the framework, what we call the pre-silicon part driving the design. And the, you get the early system hardware from your first version of the chip, and having an equivalent, part of the framework which actually does the measurements on the real chip, and be able to, reconcile those things and then drive changes into the next version of the design. Yeah. So again, key thing is really the use of end-to-end workloads, right, and not just micro benchmarks, and in the process of designing your chip, and actually use that to drive the later stages of the design. So again, the motivation again, we had several accelerators, right? With AI, we've been having standalone accelerators such as TPU, Habana, everything else. IBM announced as a part of P10, we actually have inline accelerators. So even high-performance microprocessors are being designed with inline accelerators, and P10 is one of the first such microprocessor which has inbuilt MMA, right, matrix multiply assist accelerator, and there are equivalents in Intel processors as well. Yeah. And again, there is a need for, as you kind of, first time around when you're trying to add these inline accelerators, which essentially add like additional functional units, which ISA extensions, you want to be able to completely assess, hey, what's the, what's the power and performance impact of these things as the chip is being designed, right? And in terms of contributions, what we detail here is, one is the framework itself, right? Where you can take these early workloads, complete workloads, and then run it, and then give feedback to the designer as the design is being done. And of course, reconcile it with the hardware measurements. And the key aspect here is also in using complete industry standard benchmarks, right? The ML-Perf, ML Commons benchmarks, and which are targeting inline accelerators. Yeah. And of course, using the post-silicon validation, and then using those numbers also to kind of drive further refinements into the final product, final system, which actually ships out. Yeah. So in terms of, again, a quick preview, and overview of the power and performance measurement itself. So we have the environment on which you can actually compile and run your, all your AI framework. So that we actually run on a full system simulator, right? So you have actually a disk image which does a full system simulation, and the trace generation part actually goes into a cycle accurate simulation to measure your performance aspects, CPI and other aspects. And then there is a tooling aspect which actually from that complete benchmark, when it's running on this virtual simulator, generates RTL test cases also. So there is an RTL test case for your entire ResNet 50 or BERT or whatever else you're running, and that RTL test case goes through our RTL simulation, and we have internal tools which actually use the traces to give you the feedback. So that's in a sense a setup which our logic designers, and as the MMA is being integrated into the chip, people have actually access to running benchmarks, and not just run like snippets of load and store kind of instructions, but you have actually a trace of a complete benchmark, and then they can actually assess as the chip is being designed also. So this kind of describes our very, very quickly describes the pre-silicon framework. Right? In terms of post-silicon, it's still the traditional one. We use Cronus. It's actually a low-level test tool which is actually used in manufacturing test and bring up, right? So essentially, the majority of the Cronus code runs on a companion box, the Linux companion box. And there is a small part of it which is actually on the flexible service processor also, which is on chip. Basically we run the workloads with the desired configuration, and we actually do current measurements from the Cronus setup. Right? So this is again, we use the I2C API to get these measurements, and then you get the currents for each of these voltage domains essentially, and you do collapse it back to your whole, the different functional units of the chip. Yeah. In terms of experimental results, right? So what again, one of the firsts here was use the ML Commons. I don't know how many people are familiar, but ML Commons, now ML Commons used to be called ML Perf, is an industry standard, like 50 plus, or more than 50 plus now, I guess, where they publish the benchmarks to, assess the new AI algorithms and, new hardware which is supposed to help AI. So they have it's a consortium. And there are several benchmarks there. I just show results on a couple of the more common ones, but they have several benchmarks with which you can really evaluate your edge inference performance or anything else. So we took these benchmarks, and what we did was we actually compiled it with a MMA, the accelerator-enabled library, executed that on the hardware, right? Collected the results using the Cronus approach, which I mentioned. And then you generate the traces, use the virtual pre-silicon framework, which I showed, you collect the results, and do that, without the MMA also. So now, you have a setup where you could actually compare the impact of the new accelerator, the inline accelerator, which our processor design team has been doing. And this is just this is a slide which kind of shows the accuracy of the pre-silicon. I think I didn't include it in the poster, but I just added it here so that people can have a sense of. So I'll bring your attention to just where the arrow is for the first order. The top part of it shows the performance accuracy, which is essentially you're looking at the speed up, right? Which you can see from the, on the left-hand side is kind of showing from the pre-silicon approach using the CPI measurement and the performance traces. And the right-hand side kind of shows from the hardware measurement. So you're kind of, if you just look at the BERT with the MMA, you're kind of showing a 3.6 kind of a speed up, which is kind of what you see post and pre-silicon, right? And in terms of the power, for example, if you look at the lower part of the chart where you're seeing the pre-silicon and post-silicon, where you are quite accurate with respect to the pre and post-silicon setups also in terms of power, right? That's a just a little bit of snippet on the accuracy of the framework itself. Yeah. And then the results on the MLPerf benchmarks itself. Right? Again, I probably edited it. So we generate those test cases, the RTL test cases. We run through that whole framework and then do the logic level, both activity, meaning clock gating, other metrics, which are activity-only metrics, and also power metrics, right? We derive them. And we evaluated, we are showing the BERT large model using the Stanford question answering data set. And again, with MMA, we link to the MMA optimized library. Without, we link to the SIMD optimized library. We run the simulation for 100K cycles, with first some number of cycles as warm-up. And the net of it, right, with MMA, these are results which are validated in the hardware and which our, the team which is designing the accelerators have access to this early data to show that, hey, you are consuming, 9% and 15% lower power, with the MMA rather than even without the MMA configuration. At actually I didn't edit, but at actually a 1.8 to 1.6x throughput improvement. Right? That's kind of the assessment, the overall system assessment, which our design teams were able to get. Yeah? And this kind of shows, the charts kind of show the breakdown on each unit, how you can kind of see what each unit's power consumption is. And here you're looking at the power trace with the MMA at the bottom and without the MMA at the top. Which kind of shows you're consistently at a lower point when you are using the MMA and the related instructions with the MMA. So in summary, again, the whole premise here is, hey, there's a framework, and the framework has a pre-silicon, post-silicon component, and the pre-silicon part is able to run entire workloads and give early feedback to the teams which are actually designing these inline accelerators, and so that they actually know how the design is evolving, and also validate it with the post-silicon, so that the final version of the hardware goes up, any fine-tuning can actually happen. This is really what, and this is a setup which we actually use with an IBM. That's all I have.
Thank you, Nagu. Very nice.
Thanks. Yeah, it's very interesting work. So one question is, so I see. Of course, you said you have some good correlation between your pre-silicon analysis and the post-silicon. So, but did you find anything like from a pre-silicon and also with a larger benchmark? Is there something you found good feedback you actually use? such that
So
you don't
what
need
were
to
the
wait for the
decisions?
post-it.
Yeah, what were the decisions which we drove in by this analysis, right? I should have had it, but couple of things, right? So these were both software and hardware. So the amount of precision for the DGEM-like operations, the GEM-like operations, and everything was one feedback, both from the compiler standpoint of view, which they had feedback to, and they made changes, meaning in the software and the compilation framework. And similar thing, the hardware precision when you are integrating the MMA, how much is actually needed. These were actually key changes which the design team actually made based on this kind of early analysis. Now, there are other aspects beyond that, just to say that, hey, when you are adding the MMA, I mean, first thought was, hey, when you add the MMA, you're running these unique instructions through the MMA and everything. Are you going to, in fact, increase the power or not decrease the power? So the other part was also a warm, fuzzy feeling for the MMA team to say that, yes, they're not really doing something which is out of whack, right? I mean, that's the other part of it. Design decisions driven were mainly relating to the precision and bit width on the hardware side and also the compilation framework. And the second thing was also mostly validating the architecture decision of what they were actually doing. Right? That's kind of the decisions which we drove in through the use of over stages. Right?
So on your, I think, second slide, you showed the different, you had an FPGA, you had a full RTL simulation. Yeah, it's like, this one here.
Okay.
So how predictive, how good was the prediction from, say, the FPGA emulation, which presumably ran much faster than the RTL simulation?
We didn't actually use a lot. I mean, we call it an FPGA emulation, but we have an internal simulation box which we actually did it with. So where it came out to is, that was not the focus of this work actually per se.
But you know where I'm going. It's like, the top one is really fast, but maybe not
correct.
accurate.
There's a number of cycles we could run through, right? That's essentially will be the thing, right? So here I showed probably we run for 100K, and in a lot of cases you could actually run for probably double or 3-4 times.
Right.
So there that cycle count could have been a lot more higher, but we didn't directly use it. There are some other, the infrastructure reasons where we were not able to expose this much early on in the design process, right? So we did have stable simulators, stable setup, which are actually running through your through the RTL simulation, which we could give feedback. But the FPGA with all the setup, all the libraries, and all the setup and everything else needed, we didn't use that actively because this we could give it to our logic teams, right? In a way, right? I mean, once they're done with the complete RTL, which was simulated, they could actually run this without too much amount of effort. Whereas there, I think it's the first time the chip, we didn't quite establish
you didn't necessarily model everything,
exactly,
and so on
fully,
and so forth.
it was not giving the full
and you
chip.
had to make the last one anyway, because otherwise
Exactly.
you couldn't make the chip. Okay.
Exactly.
Yeah.
Exactly.
Okay. Similarly, there's you're running your without MMA thing basically on a P9 with SIMD, right?
No, it's called P9. It's essentially a SIMD, right? So with MMA, open blast libraries have been set up. You can actually generate these instructions to exercise the MMA, right? So that's what I meant, P10 with open blast, right? So essentially we're still on,
But open blast is, so I guess where I'm going is there's another thing that you could put on the top where above cycle accurate simulation, which is just basically Excel and the code of there's this many instructions and they probably increased in speed by
You're
X.
correct. That's a back of the envelope they always do, right? But the premise here is also, can you run your full, a 3D unit with that to be able to...
Yeah,
I mean,
but
you can still get an instruction count. I see what you're saying. You can still get
and you're also looking at kind of the performance of the memory system, which will be affected by whether you're looking at ResNet 10 versus
50 versus 18
yeah.
or anything else.
Yep.
Right. Yeah.
Okay.
Yeah, I mean, the attraction of having the multiple modeling things is, some of them are going to have a very rapid turnaround.
Correct.
And so you can quickly pick, promising ideas.
Correct.
Based on the very, very high level model. This thing is clearly not as good as this other idea.
Correct.
Let's push that other one
that
through the hideously
quickly.
slow.
Correct.
Right,
because
simulation.
again, the premise here, it's the first time we were doing with an inline acceleration, right? Because now probably the next generation already has an accelerator, so the process will be slightly different. But the first time when you're actually designing with the inline acceleration, all you have is, hey, I have my micro benchmark, I have a sequence of load stores and all these things happening, but I can still cook up with the you can still generate synthetic benchmarks and do a lot, but here you get a sense of being able to go through with an entire thing. And
Right,
still
you
be
have
able to
something
do
that's
it.
more convincing
Than just the micro benchmarks, which loop, runs the same instructions on loop and such. So that's kind of what we try doing here.
All right.
Okay.
Well, thank you so much, Nagu. Let's give him a round of applause. Okay, so drum roll, please. The winner of the 59th DAC poster challenge in the engineering track is Machine Learning Techniques for PDK Development Efficiency, which was presented yesterday by Roman Foyet and his team from Global Foundries. Congratulations.
Well, I want to thank my two co-authors, Nolan Pavek and Vivian Miller, and the technical staff here that makes the magic happen. Thank you.
Yep. So we're going to present you with this lovely shield and sword. Come over here for your picture. And you also get an all-access pass for the 60th DAC next year right here in Moscone West. So let's give them another hand. Now, last but not least, as I mentioned earlier on in this presentation, this competition each year is part of the amazing engineering track here at Design Automation Conference. So I'm next going to introduce my friend Anbar, who oversees the engineering track with a grace and intelligence that is unparalleled.
Well, thank you, Brian. So I'm really so glad and want to thank the amazing work that was done by all the presenters and attendees, and also the amazing work that was done by the TPC, the Technical Program Committee. They spent, I can tell you, they spent countless hours going through each and every one. But so I really want to thank all of you, and I would like to hear a round of applause for all the presenters. Okay, so now I will be presenting two awards. One is for the embedded presentation, and another one is the IP presentation. Unfortunately, none of the track chairs could be present here, but at least I'll be doing them on their behalf. So the first one for the IP track, and I'm presenting on behalf of Randy Fish, Randy Fish, who is the IP track chair, and he couldn't make it this time. But the best presentation goes to Design for Manufacturability for Analog IP by Lin Wang from Global Foundries. So Lin, congratulations. And the next one is for the Embedded Systems track. And Mark Kraling is the track chair. Unfortunately, he couldn't travel at the last moment in emergency. So on his behalf, I'm extremely proud to present the best presentation on the embedded track, Design for Manufacturability for DFM for Analog IP, Jacob Engblom from Intel. All right. So now I would like to introduce our front-end track chair, Monica Farkash.
Hello, guys. So I also have here two prizes, two awards. I'll start with the first one, Best Presentation Award for Front-End Design. Verifying register maps with Jasper Gold, how formal compares to UVM. David Sanalitro and Eduardo Bollias, ST Microelectronics, Maurizio Martina, and Guido Massera, Polytechnic University of Turin.
Thank you.
Might use it. So the next best presentation award goes to Robust UVM Framework for Detection of Hardware Security Vulnerabilities for Security Subsystems and Cryptographic IPs. Niharika Sachdeva, Arjun Kumar, and Daniel Deshpande, Samsung Semiconductors.
Hi, everybody. I'm Natarajan Vishwanathan from Cadence. I'm the backend design engineering track chair, and I'm very glad to present 2 awards for the backend design engineering track presentations. So the first best presentation award goes to experimental validation of a novel methodology for electromigration assessment in on-chip power grids. This is by Valerie Sukharev from Siemens EDA. So do we have Valerie here? All right. So we have somebody in place of Valerie. So yeah, please, let's go ahead. But we can still give him a round of applause. Thank you. And the second best presentation award for the backend design engineering track goes to Power-Aware Scan Structure Planner by Chen Yuan Kwa, Xinhui Li, Qianchen Wu, Min Sui Tai from Global Unichip, from GUC. Okay. Looks like we don't have the presenters here, so we'll probably mail it to them. Thanks.
Well, thank you for being such a patient audience. Thank you for participating. And thanks to our awesome judges for devoting time, effort, and insight into all this work, and to all the presenters over the last 3 days who just did a fantastic job. And also congratulations to those we've just seen in the last few minutes who've won. We're done. Is there a reception tonight out here? Yes. There is a reception here, and the posters from the engineering track are still out there. So if you haven't availed yourself of that, check it out. There's a lot of interesting gems there.